Welcome to Mr. Frolic's physics classes. In this lecture, we're going to learn about some particular forces important to us. In this video, we will learn now how to look at a system and identify the forces acting on the objects into the system, which is important in order to be able to identify the laws that we should apply and to solve those problems. But before I start talking about the forces themselves, it is helpful to define a couple terms. The first term is agent. An agent would be the thing that exerts the force. Okay? The other term I would like to define is object. Is the thing where the force is applied, is the one that receives the force. In the traditional example of the foot kicking the ball, we have that the foot kicks the ball, exerting a force on the ball. And the ball reacts back with the force of the ball on the foot, pushing back on it. So, when I look at this here, for the force of the foot on the ball, the agent is going to be the one that exerts the force, that is the foot. So the foot is exerting the force of the foot on the ball. And the object is the thing where the force is applied, and that now is going to be the ball. The ball is receiving the force. For the reaction force, the force of the ball on the foot, I'm talking about this force here now. Well, the agent of the force of the ball on the foot is going to be now the ball. Because it's the ball that is acting back on the foot. And the object where the force is applied is going to be the foot. As you can see, when we talk about agent and object, for the action force, agent and object and the reaction force, they reverse roles. Okay? In a more modern perspective or more advanced view, we classify the forces as being in four types. For us here at this point, I will stick to a more basic and classical perspective. As we progress in our course, we will improve our classification of forces. So for us at this point, there are two types of forces. The first type is what we call field force. And the field force is a force where it acts at a distance. So, okay, the objects don't need to touch to receive the force. As an example, the force between two magnets, the magnetic force. The second kind of force we're going to talk about is contact force. And the contact force is a force that requires a contact to exist. So, requires contact. And for that one, I could just even use my example of the foot kicking the ball. So, this was our very first classification of forces. The first force we will study now is the gravitational force, which in our daily lives we call weight. Okay? So my situation, my example is, for example, the Earth and then the Moon. moon orbiting the Earth. The gravitational force is, to start, a field force. So, the gravitational force acts at a distance. I don't need contact for it to exist. Number two, it is an attractive force among masses. So, the mass of the Earth attracts the mass of the moon, exerting here a force of the Earth on the moon, and then the moon reacts back, exerting a force of the moon on the Earth. All masses in the universe are attracting all masses. Right now, you are attracting and being attracted by your computer screen, your phone, your pens, your papers. But the gravitational force is a weak force. It only becomes significant when at least one of the two objects involved in the interaction has an astronomical magnitude, astronomical size. So it's meaningful when I'm talking about the force of the Earth on me, of the moon on me, or of the sun on the Earth. But not really meaningful when I'm talking about the force between my two markers, the attraction between my two markers. Another important property for us to consider is we can consider the force concentrated in a single point. This point is usually called center of mass or center of gravity. You see this here. This mirror stick has mass all over it. But I don't need to hold it this way to balance the attraction of the Earth on the mirror stick. I can get just one point roughly here, and I can completely balance the mirror stick, the weight of the mirror stick, by just hanging by this single point here. Okay? So it works as if all of the weight of the mirror stick was concentrated in this one point. This one point we'll then call center of mass or center of gravity. If the object has a regular geometric shape and uniform density, the center of mass is actually located in the geometric center of the object. Okay? Now, one thing I would like to discuss is this. In our daily lives, we don't really see the Earth from that far away perspective. We really concentrate our focus in a small region near the surface of the Earth. And when we look on this perspective, when we zoom in to this level, the surface of the Earth looks like a flat surface. Okay, it looks like something flat. And more than just flat, it seems to be unlimited. As we look, as you go to the horizon, the ocean, and you look far, you don't see the edge of the world. Okay, you just see the point where the ocean seems to touch the sky at the horizon line. But as you move forward and forward, that touching point keeps moving away and away. So you never actually get the limit, the end of it. And when we talk about a small object, like a rock, perhaps, that rock is being attracted by the Earth, okay, and that will be the force of the Earth on the rock. And in our daily lives, we actually call this here the weight of the rock, okay? This force is going to be vertical and pointing towards the center of the Earth. And it is applied at the center of the rock itself. the reaction force to this force is going to be a force of the rock on the earth, pulling the earth up. Okay? But usually we don't represent that one because we're not interested in studying that one. Just now to adjust, from the force of the earth on the rock, the agent is the earth and the object is the rock. But the force of the rock on the earth, the agent is the rock and the object is the earth. When I talk about moon and earth, for the force of the earth on the moon, the agent is the earth, the object is the moon. Force of the moon on the earth, the agent is the moon, and object is the earth. The next force we're going to study is the force transmitted by a string. And this force transmitted by a string is usually called tension force. In order to understand tension force, I will also use this example to develop with you a couple new concepts and to build a how to solve problems. So the scenario that we're going to imagine is this here. We have our classroom. The classroom needs to have a high ceiling because it's a large environment and we need a high ceiling so the air can freely circulate. So here's the high ceiling. Then I need to put light fixtures to illuminate the classroom. But I need those lights fixtures to be relatively low down so I can produce the proper brightness at the desk level so we can read properly what we're doing. We have two choices. We can put the light fixtures way up here and use very powerful light bulbs, or we can hang them by a wire, and then this is my light fixture. Okay? In my example here, let's say that I want to hang a 5 kilogram light fixture and that we use a wire with 1 kilogram of mass. So before I start doing the standard approach, I would like to introduce us to the idea of system. On a system schema, what we do is we represent the things that are meaningful in our system and their interactions. So, for example, my system schema in here, what's important is earth, wire, light bulb, ceiling. So what I have in here is this. The wire is connected to the ceiling, okay, and it is also connected to the light bulb. And it is connected to the earth because the wire has a mass, so it's being pulled down by the earth. The light bulb is connected to the wire and it is connected to the earth. And, well, the ceiling has mass. It should also be connected to the earth. Although, unless there is a concern about whether or not the ceiling would stay in place, whether or not the walls would be able to hold the ceiling in place, we are not really that concerned in studying the ceiling. My concern more would be, for example, how strong of a hook I need to fix on the ceiling in order to hold the system, rather than whether the ceiling would actually stay in place. So we usually stop at this point. Remember, we need to consider in our analysis the part of the system that matters. Otherwise, we never would be able to end any problem, solve any problem. Looking at this system schema now, I see that the light bulb has 1 and 2 forces acting on it. Each connection represents an interaction, and each of those connections will tell me one force acting on an object. When I look at the wire, I see that the wire has 1, 2, 3 connections. So the wire should have 3 forces acting on it. Finally, when I look at the ceiling, I have only 1 connection that is meaningful for me, so I should have just 1 force acting on it. I'm going to start doing what we call to be a free body diagram, in which we represent the objects of my system in separate, and then we plot the forces acting on them. So the first and the simplest object is the light fixture, is the one at the end. And that's the one I should actually use to start my study. So the first object we should consider is the one that's the easiest, the simplest part. And I would say then that we should start by the light bulb. Well, the light bulb has two connections, therefore two forces act on it. The first force is going to be a force of the earth on the light bulb, and that is the gravitational force of the force pulling the light bulb down. It should start from the center of the light bulb, be vertical down like this here. Force of the earth on the light bulb. Now, I know that I have a second force acting on the light bulb, and at the same time, this light bulb is at rest. It's not falling. So the total force on it, the net force, must be zero. The only way for that to happen is if the wire is exerting an upward force. So that's going to be now a force of the wire on the light bulb. And this force of the wire on the light bulb must be equal and opposite to the force of the earth on the light bulb. It must cancel it. And Newton's first law would allow me to make the statement that the force of the wire on the light bulb equals force of the earth on the light bulb. And considering my mass of 5 kilograms, that will give me, assuming the acceleration due to gravity to be 10 meters per second squared, about 50 newtons. The next object on my system here now is going to be the wire. So here is a representation of the wire. And let's start now talk about the forces acting on the wire. The wire has 3 connections. One to the earth, one to the light bulb, and one to the ceiling. So the force of the earth on the wire is in here, vertical down, starting at the center of the wire. Force of the earth on the wire is down here. The wire was exerting a force up on the light bulb. Therefore, the light bulb would also exert a force down on the wire. Here is a force of the light bulb on the wire. Based on Newton's third law, based on Newton's third law, the force of the light on the wire equals the force of the wire on the light, and that must be then 50 newtons. Okay? Now, this wire is also not falling, is at rest. So there must be a force up that balances the two forces down. And when I look at my system schema, that force up must be coming from the ceiling. So we're going to have now in here a force of the ceiling on the wire, pulling up. And that force of the ceiling on the wire, according to Newton's first law, will be canceling the force of the earth on the wire plus the force of the light on the wire. Considering that the force of the earth on the wire, I'm assuming the wire would have a mass of 1 kilogram, so this one force is 10. The force of the lamp on the wire, we saw, is 50 newtons. So the force of the ceiling on the wire would then be 60 newtons. I'm almost finished. Now let's go to the last object to consider, which will be the ceiling. And I'm running out of space, so I'm going to write this one here on this corner. So here's the ceiling, and I basically only need to consider this. The ceiling exerted a force up on the wire. The wire would then now exert a force down on the ceiling, like this. And Newton's third law allows me to write that the force of the wire on the ceiling equals force of the ceiling on the wire, and that is 60 newtons. So what we did in here was an analysis on the system schema, then the free body diagrams, and after that I wrote the laws and the equations. And we could answer the question, how much of a force I have up here. What you can notice is that because the wire has a mass of 1 kilogram, the force at the ceiling where I need to put the hook, the required force is going to be stronger than the actual weight of the lamp I want to hold. When we studied our light wire system, we saw that the force required to hold the system in place at the ceiling, as if I was putting a hook in there, is actually bigger than the weight of the light that I want to hang. This happens because I need to take into consideration the mass of the wire. But the wire is just an auxiliary method. It's just something I want to hang up down there. And if I make this wire lighter, instead of 1 kilogram wire, I use 100 grams wire or perhaps 50 gram wire, the force up here is going to be almost the same as the weight of the light bulb. This brings us then to what we're going to call now the model of the perfect string. So, perfect string. And every time I use the word perfect, I actually mean then that this is a model. Model is something that I am simplifying. I'm getting a real situation and simplifying, making some assumptions. So for the perfect string, my assumptions are basically that, 1, it has negligible mass. So my perfect string is basically massless. Number 2, it doesn't stretch, which means that if I make the top, by any chance, move a certain distance, the bottom of the string, the other end of the string will move the same distance. Now, when I represent this system, considering these models in here, my systems can be reduced to this: ceiling, a perfect string, the light bulb, and then I'm going to have a force of the earth on the light bulb, which is again the gravitational force of the earth on the light bulb. The agent is the earth, the object is the light bulb. Then I'm going to have in here a force of the string on the light bulb, and up here a force of the string on the ceiling. And since I'm assuming that the string is massless, those two forces are supposed to be the same. So the forces on opposite ends of a perfect string would always be the same. And these forces here are actually what we're going to call tension force. Okay, so the tension force is the name we're going to give to the force that the string is exerting on the objects, on each end of the object. Now, every time we talk about a model, we know we are simplifying, we're not getting the perfect answer. The question really that we need to discuss is not whether or not a perfect string exists. It doesn't. But how good this model is. And a good model will produce for us results that agree with observation within an acceptable error. So, for example, fishing line and go fishing. A couple meters of fishing line has a mass of the order of a couple grams. Now, you go fishing and you use that fishing line to fish out of the water a fish that has a mass of a couple kilograms. So the mass of the object I'm hanging is a couple thousand times the mass of the line itself I'm using to hang. When I go to weight the fish, not considering the mass of the fishing line produces an error on that situation that is most likely less than the precision of the scale itself. So, for that situation, the model of the perfect string is an excellent model. It produces results that agree with my ability to observe stuff. It introduces an error that is smaller than the error of my scale. The third and last kind of force we're going to study today is the contact force. Now, when we talk about the contact force, we have two kinds of contact to consider. The first one is what we call a rough, I think it spells like this, surface. And the rough surface is the surface that we encounter in our daily situations. It's the floor, the table, our shoes, okay, the tires of a car, all of that. So let's start discussing then contact on a rough surface. And I'm going to split that into two situations. Situation one is no sliding tendency. So let's consider that we have this here, the floor, and a chair sitting placed on that floor. The system schema for this system here is my major object, the chair, the floor, and the earth. And the chair is sitting on the floor, and it is being pulled by the earth. And again, of course, that the floor also has a weight, is also being pulled by the earth, but usually we don't consider this one here. So under this analysis, on the chair now I have two forces acting on it. I'm going to represent now this chair, but in separate on my free body diagram. So I have in here the chair, and then the floor. The forces acting on the chair would be, first, a force of the earth on the chair. That force of the earth on the chair, the agent is the earth, the object is the chair. The reaction force is a force of the chair on the earth, where the chair is the agent, the earth is the object. I'm not going to represent because I'm not interested in studying the earth. Now, this chair here has a tendency to fall, but it is at rest. So there's some force up, holding it in place. And I still need to account for a connection of the floor. So what I'm going to have is, in the upward direction here, a force of the floor on the chair, holding the chair up. And if I have an action of the floor on the chair up, I'm going to have a reaction force of the chair on the floor down. Okay, here should be F for floor. So this is the free body diagram and the forces acting on the chair. Notice that the agent of the force of the floor on the chair is the floor, the object is the chair. Here's the reaction, chair, floor. Notice more, the force of the earth on the chair is not the same force as the force of the chair on the floor. And this force of the floor on the chair in the future is going to be called normal force. We'll still going to address that. From an equation perspective, Newton's first law would allow me to say that the force of the floor on the chair cancels the force of the earth on the chair, and Newton's third law would allow me to say that the force of the floor on the chair is equal to the force of the chair on the floor. It is important to know which law I'm using, because a small change in the system may change some of those equations. If someone sits on the chair, the force of the floor on the chair is no longer going to be the same as the force of the earth on the chair. But the force of the floor on the chair would still be the same as the force of the chair on the floor. So we need really to know why we make each statement. Let's now consider a small difference here, which is a sample 2. Now, sliding tendency. So example 2, let's say that the chair has a tendency to slide. How is that happening? Well, there is a hand pushing on the chair here. So now there's a hand pushing on the chair sideways. Although that hand is not pushing hard enough, that will make the chair move. So the chair stays what it is. My system schema needs to be now amended for that. So I'm going to add here a hand. And I have a third connection on the chair, which means that now I need to explain the chair staying in equilibrium using 3 forces instead of only 2. The hand most likely has mass and would have a connection with the earth, but again, I'm not interested in that one. Let me repeat now here my free body diagram for this new system. So here is my chair, and here is the floor. Well, the first force I'm going to consider in here is this new force of the hand on the chair. So it is pulling the chair sideways, like this. Force, hand, chair. The agent is the hand, the object is the chair. The reaction to this force is a force of the chair on the hand. The hand is feeling back that force, but I'm not interested in studying the hand. So I'm going to stop here. The next force I'm going to consider is the force of the earth on the chair. Well, the force of the earth on the chair, the agent is the earth, the object is the chair. The reaction is a force of the chair pulling up on the earth, and again, it's acting at the center of the earth, but I'm not interested in studying the earth. I'm not going to bother with it. Finally, I need to account for the force of the floor on the chair. Well, in here, we have 2 forces already. I need to add one more. This third force needs to balance the 2 forces at the same time. It needs to balance the tendency of the chair to fall because of the pull of the earth, but also to slide to the right because of the force of the hand. And the only way that can happen is if the force of the floor on the chair becomes a slanted backwards force. If we consider that, then the reaction force down here is going to be a force of the chair on the floor, and that's going to be slanted forward. So you see that this contact force of the floor and the chair is not as simple as the other force we studied before. When there is no sliding tendency, this force is 100% perpendicular to the surface, and we will call that just normal force. When there is sliding tendency, that force is going to be slanted back. It is a little bit up, and the a little bit up component, let me repeat that picture here. We will still call normal force. The difference is that when the chair tries to slide on the floor and there is grip, it is a rough surface, we're going to have friction. That's going to hold the chair in place. And friction is actually what makes this force be slanted. You guys will find in most books that they don't really write it this way. They will call the total force of the floor, and then they just go straight into normal and friction. And when we actually start doing calculations, that's how we're going to do this. To finalize our study of contact force, we'll now talk about second kind of contact, which is a smooth surface or slick surface. Now, In physics, a smooth surface or a slick surface really means completely no friction. It's a perfectly smooth surface. And every time we talk about perfect, we talk about a model. So, in this situation here, I will consider the floor and a chair on the floor. But just to make it easier for us to visualize, let's imagine that this chair now is on wheels. Okay, perfectly frictionless wheels. If I analyze this system as is, my system schema will be the same as before. It would still be chair, floor, and earth. And I still have two connections to the chair. So my free body diagram for this system is going to be the same as before. If here is my chair, and here's the floor, I'm going to have a force of the earth on the chair. Then the chair will exert a force down on the floor, force of the floor on the chair, and then the floor exerts a force up on the chair. And I can perfectly explain the equilibrium of the chair this way. If now I had the hand, things complicate a little bit. Let's add the hand in here. I'm now going to have three forces acting on the chair. A third connection is present in here. But the thing is, if there is no friction, no grip to hold this chair in place, this chair will accelerate when the hand pushes to the side. There is no way that this chair is going to stay at rest. So when I add my force of the hand on the chair here, that contact force will not make any change. Remember, the contact force got slanted back because friction appeared in here to hold the chair in place. But on the model of the no friction surface, basically, I cannot have this friction, and then that force is not going to get slanted. The discussion now that we should have is not whether or not this exists. It doesn't. A perfectly frictionless surface does not exist. But how good of a model that is. And the non-friction model is going to be good if you really have well lubricated surfaces, the air track, with a little layer of air, and really only on a relatively short range. So this model, although it can be used in limited situations, is not as good as the perfect string model. Well, this concludes our lesson about some particular forces. The next step now should be work problems on free body diagrams and also identifying the agent and object of several forces. See you next time.